Welcome everybody. We are going to talk about elimination reactions. Elimination, what does that mean? Taking off two substituents to make a pi bond. That's really what elimination is all about. So elimination is the opposite of addition. Here you remove or removal of two substituents, and most of the time the substituents are adjacent to each other to create a pi bond. Okay, so all eliminations result in a new pi bond. Now, if you can do that in one step, that's typically a bimolecular reaction. If you have multiple steps, then it's a unimolecular reaction. Now, this bimolecular reaction E2 is what we're going to look at today. Elimination, bimolecular, that's what the 2 is for. Okay. All right, so here, let's look at this example. We have a potassium hydroxide reacting with an alkyl halide. Again, these are just reactions of alkyl halides. Before we do that, let's do a very simple elimination with a molecule here. For example, let's say I have an alkyl halide like this. And it could be an iodide, bromide, chloride, some leaving group. And we have here a chart of your leaving group and the pKa's of that. Lower the pKa, better the leaving group. That's a very important thing here. Leaving group ability is going to affect the rate of this reaction. Let's say we add to this a base. Any base, the base that you've typically used so far in Gen Chem is potassium hydroxide. And earlier we saw how it did a substitution. But when you have a good, strong base, bases also love hydrogens. And if they're steric, then they're quite happy pulling off a hydrogen and creating a pi bond. All of this happens at the same step. So therefore, you're going to have a transition state for this, just like in your SN2. All your 2, SN2, E2 are bimolecular reactions, which means they're concerted. So in your concerted transition state, you would have your hydrogen being broken and your iodide being broken at the same step. That's why it says removal of 2 substituents to create a pi bond, not just one. Now, here's your potassium hydroxide, and that has to come in to pull off the hydrogen. Hydrogen can't just take off on its own here because it's really held by the carbon, quite tightly. It's a strong CH bond. You don't see CH bonds just breaking and falling apart, or CC bonds for that matter. You need a strong base to rattle that bond and pull it off. And so those electrons from the hydrogen are given over here. That is going to then break up this Ci bond, and the iodine leaves. The iodine is tugging at this bond, and that becomes a delta plus, which is what's pulling these hydrogens, and the hydroxyl then helps that hydrogen to leave by making a bond with the hydroxyl to that, making a very stable water molecule. So this is your transition state, and in the transition state, 2 molecules are involved. That's why you have this 2 here, E2, bimolecular. Now, once it leaves, then you have a pi bond, which is what we said before. It creates a pi bond. You also have your iodide leaving, probably with your potassium here, and you would also create water, which is a very stable molecule, and so the thermodynamics of this is also favored. So it is kinetically, fast when you have strong bases. How do you know it's a strong base? Look at the pKa chart. Typically, it's got to be above 12. So some books may say 11, somewhere in that region. And you can see here 15, 16, and so on, all the way to almost 40 for the hydrides. So hydroxide, methoxide, ethoxide, third butoxide, amides, hydrides, even acetylides, a lot of these have pKa's above 12 for their conjugate acids of these anions. So those are really, really good bases. If you want to do an E2, you gotta have a strong base. Otherwise, it ain't gonna do an E2. All right, it's not gonna pull off that hydrogen unless it's very strong. So here we have a strong base that pulls off the hydrogen, and that makes a pi bond and releases the iodine. Now, when you have three things coming out, well, you know, when you have lots of molecules, your entropy goes up. So temperature goes up, plus delta S goes up. Delta S gets more positive, then your delta G gets more negative, which means it's going to be more and more going to the right spontaneously as the temperature goes up. So temperature always favors elimination. So that's one of the things that you have to remember, is that elimination is a process by which you take off two substituents to make a pi bond. Both the substituents coming off at the same step with an external agent, which is a strong base, would lead to a bimolecular elimination, E2. So there are two components to this transition state. One is the Rx, and two is the base. Now, we could also put this anion outside and put your potassium out. That's another way to write it. Now, if you take this and look at all the things that are involved in here, rate is going to be proportional to the concentration of this and this, because they both have to collide. The more of them you have, the more they would collide, right? If you have only 10 of them, then they got to search for each other in the dark. Where is it? Where is it? But if you have millions of them, they're just going to be colliding. So the more of this that you have, the rate's going to be higher. So your rate is going to depend on your Rx. And the Rx has got two parts to it, R and X. And it also depends on your base, in this case KOH, or I would say base. Now, the base, the cation really doesn't matter. It's just a spectator. It's just coming to see the game. It's the base that's here that's really involved, the anion that's really in here. Okay, so you have to have a good, strong basic anion and an Rx that's going to be allowing this to happen faster. Now, if you look at this, this is electron deficient in the transition state because iodine is literally pulling off those electrons and running away with them. So whoever can donate electron density to that transition state, they will stabilize that. So this is all about bringing down the activation energy so that your rate is going to be high. That's pretty much it. So your R would be more substituted, it would be faster. Tertiary, better than secondary, better than primary for Rx. More substituted pi bond will bring down that activation energy. Reduces activation energy by stabilizing incipient pi bond. That's really important. Well, there's another part to it, X. That's also going to influence it. Every single thing in this transition state is going to determine how fast this is going to be. X is the leaving group. In this case, iodide. And you can see, we can say what a good leaving group is just by looking at a pKa chart. There's nothing to memorize here. You look at a pKa chart, lower the pKa, better the anion, is at taking off or leaving or breaking away. Because it's more stable, that's why the pKa is low. It's more acidic. Therefore, we can say that iodide would be a lot faster than bromide, bromide more than chloride. Fluoride is really not a good leaving group. We saw that before. And there are lots of OTS and other leaving groups that are also really good. Leaving group stability is determined by pKa. Lower the pKa of the HX, better the leaving group. In this case, we are calling that the X. So that's really important. Of the three things, alkyl group, iodide, and then the base. How do we know something is a good base? Base is basically the pKa. pKa typically should be above 12, maybe 16 and above. Usually is what we use. 15 and above is what we typically use. Sodium hydroxide is like 15.7. pKa should be high. So just like the leaving group pKa should be low, the base pKa should be high. And you can see that you can, the hydroxyls, then methoxide, and more R groups you have, the oxygen is going to be more and more, basic, wanting more electrons. And then we also see things like acetylides, amides, hydrides, those are very basic. So pKa should be very high. And those are the three things that are in the rate expression. So if you double this rate, will double. If you double this rate, will double. If you double both, it'll be quadruple here. You've been through all that. So over here, this is a starting material. And so let's say this is your delta G, or let's say your delta H, so let's say this is your energy, and here is your reaction coordinate. And this initially would have some energy. We don't know what that is. It depends on the molecular stability. And let's say we take these and we add them together, and then you are going to have a transition state. So bam, you're going to go up. And then you're going to come down to make your product. And the activation energy here is what we are talking about, because we're talking about kinetics. Lower the activation energy, higher the K and higher the rate. And so these are the things that really help make this elimination reaction faster. And of course, all your side products, and I'm just going to write it like this, H2O. All your side products are going to be here. Let's look at this principle applied over here and see what we're going to get. All right. So here is an alkyl halide, and you're going to get KOH. KOH is going to come in here. First, it'll try to do a substitution. Too much steric there. So then it's going to go do an elimination. So here's your leaving group. So let's draw the leaving group out like this, because it has to go and align with the hydrogen next door. If there is no hydrogen next door, let's say you had another methyl group, there won't be any elimination there because there's no hydrogen to pull off. So beta hydrogen is key. You don't have a beta hydrogen, you got no elimination. You got to have this. Then you're going to have two methyl groups over there and two methyl groups over here. Okay, so tertiary, obviously, you're not going to get really any substitution over there. SN2, no backside attack, is too crowded. So it's going to go for your beta hydrogen. Is that the only possibility? Well, whenever you have an elimination, drop a line from the halide to the carbon and check out all of the neighbors. You got neighbors here too, not just there. Now these hydrogens, those are too far away. You got to be right next to beta. This is alpha, beta, that's it. So here you have CH3, CH3. You have 6 hydrogens here. So that's also a possibility. So you would think, well, there's only 1 hydrogen here and 6 hydrogens here. So your base is going to go over here, pull these off. Let's see what happens. Let's see what the results are. So according to the results, you would think this is 6 times more than this if it is just statistical, right? So let's look at that. This is what we get. So if you put a double bond here, which is here, you get 4 of these sticks on that pi bond. If you put a double bond here, then you'll have a methyl and an isopropyl on the other side. Let's see which one is formed. So statistically, this should be 1 to 6. But experimentally, this is 4 to 1. 80%, 20%. Okay, so completely opposite. Why is that? Even though you have 6 accessible hydrogens, why is it going out for this lone hydrogen way out here and it's got a lot of steric? Well, as we said before, it's not attacking here, so steric is not really an issue here. It's the stability of that transition state that really matters. If you pull off a hydrogen here, you got 1, 2, 3 carbons donating. If you pull off a hydrogen here, there's 2 hydrogens and only 1 R group. That really matters here. Okay, so that's the key. So having more substituents is going to be the better path to go. So here's your hydroxide. That's going to pull off this hydrogen. Those electrons are going to go into that carbon, alpha carbon, and kick out your bromide with the electrons. So let's draw the transition state for this. The transition state will have this hydrogen coming off, and it's going to be tugged by this hydroxyl. Lone pair literally pulling out that hydrogen. Now those electrons are going to be running into this carbon and making a pi. Now that has got 2 R groups and 8 electrons. If that comes through, someone's got to leave. It's just way too many for that molecule to handle. So your bromide says, hey, I'll be quite happy without all of these carbons butting heads. Let me get out of here. And so that's what it does. It leaves. And all of this happens at the same time. It's a concerted reaction. And there are 2 molecules involved, this and this. So this is bimolecular. And they have to leave. So water is leaving, bromide is leaving. Everyone says, I want out of here. So that's why we call it an elimination. Elimination always creates a pi bond. So 2 substituents are removed, bromide and the hydrogen, to create a pi bond. So that's exactly what we're doing here. We have a rule for this. The more substituted alkene is always preferred, and that's called the Zaitsev rule. So this is your Zaitsev product. Why is Zaitsev product the dominant one? That's because in this transition state, we have 4 R groups donating into that, and even more than that, you have a lot of hyperconjugation. So all of those donate electrons into this system to stabilize the pi, and it brings down the activation energy, so it just all jumps over really quickly. We're talking about kinetics here. As we can see here, if I pull off this hydrogen, your transition state here, and I'm just going to draw this and I will take it out because I don't have space. Your transition state here would have a hydrogen leaving, and that's attached to 2 hydrogens, this carbon, and the next carbon is the one that's got a bromide. So you have a bromide leaving here and a pi bond forming here. All of this is not going to happen on its own. This can stay inside a bottle forever until you put in a hydroxide or a ethoxide or a third butoxide or some base. You can see here, this pi bond that's forming has only hydrogens on this side and R groups here. So it's going to be di-substituted. This has got 4 friends donating in here. This has only got 2, you see. So you would think it would be half. But in the transition state, energy decrease has a huge impact on the product distribution. Even a small reduction in the activation energy leads to a much higher proportion in the products. This is then going to give you a pi bond right here, and that's your product. So this is your minor product. And the one that's the opposite is usually called the Hofmann product. But this is a Zaitsev reaction. So some of the things to pay attention here. One, the leaving groups should be opposite or anti to each other. Why is that? You need to have these p orbitals that are forming on the same plane. So here your hydrogen is going to leave, and that's going to create a p orbital. The sp3 becomes a p, and here the bromine leaves, and that sp3 becomes a p. So these, when they become a p orbital here, these sp3s become a p orbital, they got to be in the same angle, in the same plane. So therefore, they have to be opposite to each other. Now the base cannot come in from the same side as the bromide. So it always comes in from the opposite side to sneak out, catch that hydrogen, and it has to align in the opposite direction. So those p orbitals can overlap. So that's very important. Two, you got to have two things in that activation energy transition state. So here's your transition state. It happens all at the same time, so it's concerted. So both Jack and Jill have to go up the hill at the same time. Jack going up there is no use. You got to have Jill along to pull off that hydrogen and make that pi bond. So all of those things are really important. Now, this is only going to get really fast if you have a really nice strong base and good leaving group and a very substituted alkyl halide. Those are the things that are going to make it faster. All right, let's take another example here. Here's a base. It's a good base, strong base, alkoxide. And, well, these actually, most of the E2 bases come in protic. Unlike SN2, where you have aprotic being so much faster than protic, these typically can go in aprotic or protic. Now, if you take this alkoxide, you cannot do an SN2, obviously, because this is tertiary, and here's a tertiary alkoxide. You know, there are going to be really butting heads. So no SN2. Well, what's another possibility? Then we can talk about E2, just like over here. So now, if you're going to do an E2, your base is going to come in, well, can attack here. So it has to do with just pulling off hydrogens. It's just going to do, okay, take off these hydrogens and do an elimination, just like over here. So, well, we just said it wants to pull off the one that's more substituted. Now, this t-butoxide is going to have a problem with that because it's so big and it's so bulky. It really can't get in here because of all the steric. So mainly for sterical reasons, the t-butoxide is going to stand on the side and pull off that hydrogen and run with it. Okay, so we are going to flip the roles here and say, when you have a huge base like a t-butoxide, there are other bases too, like DBU and DBN that can only do E2, and that's going to be on the less substituted carbon. Okay, of course, this is going to be energetically favored, but because of all the steric, can't get in there. So it's going to have to do with these small hydrogens on the side. So in this case, so here, this bromide is going to leave with the less substituted for the major. So you can say, well, you can do these or you can do these. They're all identical. Your t-butoxide does the exact same thing as before, comes in and pulls off that hydroxyl or the hydrogen that is going to be anti to that bromide, and that is going to pull off that bromine. So over here, let's draw the transition state. Your t-butoxide is going to pull off that hydrogen. That hydrogen is going to have to let go of that carbon, and all those electrons are going to run along, and it's going to go into the bromide. So the bromide is now going to have an octet, and that's the only reason it's going to leave. That's your transition state. Now I could put the minus here, and well, if it's a minus, it's actually spread through the whole thing. So I can also put it out here, and put a counter ion. This is going to give you a pi bond right here. Your bromide's gone with your potassium. It's going to fall out. The more it falls out, the more it's going to go to your right, and your hydrogen is going to take off with your T-butoxide and become an alcohol, T-butanol. So now it's not going to dissociate anymore. Now over here, this is going to be having two hydrogens, which is like the downside of that. That's not really very stable. It is high energy, but since you have these huge bulky methyl groups, we don't have much choices here. The other minor product here would be the one where we are pulling off this. So if I label this A and label this B, this is going to be A. That's going to be your major product. And this is going to be B, and B would be putting a pi bond right here and having it tri-substituted product. All right, let's look at this reaction here. It says cyclohexane. Now this is going to be having a hydrogen here. So you know it's secondary. So it's less substituted than a tertiary. So it may be a little slower, but it goes really well when you have a good base, strong base. As I said, when you have an anion and a neutral, ignore the neutral and go with the anion. That's for SN2, E2, or even for SN1E1. Okay, so always go with the anion. So when they took these two, they found that one of them is going to be a lot faster. They're going to give different products. So when they did the experiment with the ethoxide, they got different products. Now you would think this is a small base, not sterically hindered like that. So the small base is going to do a Z-Zef elimination, and you would get a pi bond right here. That's tri-substituted. Let's see what happens. Let's call this A and let's call this B. Let's draw the chair form for this. So if you draw A in a chair form, methyl up, bromide down. Now it's really important when you do eliminations on a chair that the groups that are being eliminated, the two substituents that are going to come off, are both axial. And why is that? That's the only way that those sp3 will become P's and align in an angle parallel to each other to give you a nice pi bond. So here you have a bromide coming down and a methyl sticking up, which means it's axial. Now, in this case, the bromide needs to have another axial hydrogen. There is no axial hydrogen here. Where is it going to get it from? Well, it looks around. It's never going to eliminate. None of these eliminations are going to happen where you're eliminating the hydrogen that's on the CX bond. Never, because if you make that anion, there's no way for it to go. It's on a different angle from that bromide. Okay, so don't ever remove the alpha hydrogen. It's all about beta. There's one beta here, and remember there's another beta here, and this can have a hydrogen. So your ethoxide is going to pull off this hydrogen, and that's going to create a pi bond right here that is less substituted. We just don't have choices here. So now that is going to give you a pi bond on this carbon. It might be a little easier to see if I draw the flat version. So your pi bond is right here and your methyl is up here. So this inadvertently produces the Huffman elimination product, even though it's a small base, mainly due to this restraint or condition that leaving groups must be diaxial. And that's because of the angle. They got to be parallel in order for those to overlap and form the pi bond. Let's look at B. So this is your A. And let's look at B. What happens in B? Let's draw out B. So if you draw the B out for this molecule, again your methyl is down and your bromide is down. Now where are the axial hydrogens? You have an axial hydrogen here and an axial hydrogen here. Great, which one are you going to go for? It's a small base. Steric is not the problem. So it's going to pull off the one that has more substituents, so your activation energy can come down. So it's going to go for the hydrogen on the most substituted carbon. That's going to push those electrons down to that bromide, and that's going to take off. This would then give you a cyclohexene, where the pi bond is on the same carbon as that methyl. So this is your actual Zaitsev product. Okay, so this is more stable because it's tri-substituted. This is di-substituted. However, as we said before, because of the diaxial constraint, there is no other choice for that. That's your major product. One little thing before we wrap up E2. Here is a no-born-in type of compound, and you have a chlorine right at that junction. Can you do an E2 with these bases, or can you do an SN2 with these small nucleophiles? This is a nucleophile and a base. Let's look at it. Well, the backside's really covered by like a couple of layers there, so no backside attack possible over there. E2, well, if you take this, you can see there are hydrogens here, hydrogens that are beta, and hydrogens that are beta. 6 beta hydrogens, so that should be good, right? But what happens is when you pull off this chloride here, the hydrogens and the chloride orbitals cannot align to form a pi bond. So when you have a nice, good, strong base and a good leaving group, you still can't do it, mainly because of the sterics and all the restraints for the angles. So there's no SN2 and no E2. So this is quite unreactive. You can do SN1 and E1 if you have protic solvents. You can take that off, and then you can hammer that with nucleophiles and do SN1, E1. But if you have a strong base and you're looking for SN2 or E2, ain't gonna happen. You could get SN1. Okay, even E1 is going to be a problem because of the angles. So you would have mainly SN1 is okay. So Brett's rule states that if you have a bridgehead halide, like here, no E2 or E1 for ring size less than 7 carbons. Okay. 7 to 3. If it's greater than 7, 8 carbons in Taxol synthesis, they had an 8 carbon ring with a bridgehead, and that was okay. But if it's less than 7 or 7, you cannot have a bridgehead pi bond. So let's look at all the possibilities here. If your Rx is going to be primary and you have a small base, it's going to do backside attack, and you're going to get SN2 mostly. If your alkyl halide is secondary, then even with a small base, you're going to get E2 more than SN2. If your alkyl halide is tertiary, lots of steric, this is going to do mainly E2. If you have alkoxides, and if it's a small base, let's say this is a small base, like ethoxide, methoxide, and so on primary, you're still going to get SN2, but you would also get E2. And with a small base, you're going to get a lot more E2. I'm not going to write out the SN2. And on tertiary, you will only get E2. Now, if you have bulky bases, even on primary, you're going to get E2. And it's going to be more than SN2. Now, if you have secondary, you are going to get pretty much all E2 with a bulky base. On tertiary, there's absolutely really no question about SN2. You're going to get E2. A bimolecular elimination reaction, you got to have 2 molecules coming together at the same time. They need to collide. Then on that collision, it all has to happen at the same time. It's considered you pull off the hydrogen, which forms the pi bond and releases the bromide. So both these are really very important to determine how fast it's going to go. If you have a very highly substituted alkyl halide, those R groups are going to donate electrons through hyperconjugation and inductive effect. And so therefore tertiary is going to be faster than secondary, that's going to be faster than primary. If we have a good leaving group and it's going to just take off in a, jiffy like that, that's also going to make it faster. So if your pKa is low for the conjugate acid, that means the anion is going to be a really good leaving group. Now, another thing that's important in that equation, rate equation, is going to be the base. So here the rate is going to be equal to K and the Rx and the base. So both the Rx and the base are going to influence the rate. Base pKa should be high, typically higher than 12. The higher it is, the faster it's going to be because it's going to be a very strong base. The smaller the base, faster the rate. Some of the bases would only do E2. Now, if you have certain restraints like in a chair, you have to make sure that the leaving groups are diaxial so the orbitals can overlap to form that pi bond. And if you have a halide on the bridgehead, it's not going to eliminate unless you can form a ring that is more than 7 carbons. So a couple of things here. One of the things that I'd like to talk about are the factors that affect E2 reactions, bimolecular elimination reactions. Well, you can see in the rate expression, there is a alkyl halide and a base. So when you double this, then the rate would double, or if you double this, then the rate would double. If you double both, then the rate would quadruple. And that was the same with RSN2 as we saw earlier, because that was also a bimolecular reaction where in the rate determining step, the slow rate determining step, 2 molecules are involved making and breaking bonds in a concerted way. So that is really key. So let's look at each one of these. If you take the alkyl halide, there are 2 parts to it, the alkyl part and the halide part, or the leaving group. Now, it doesn't always have to be a halide. It could be a mesylate or a tosylate, any of the, or a sulfate even, so many good leaving groups out there. So since we're talking about alkyl halides in this chapter, we're basically looking at, iodide, bromide, chloride, and fluoride. So how do you determine each one of this? First, in the case of your alkyl group, tertiary is going to be faster than secondary, faster than primary. As we mentioned, here we are not doing a backside attack, so the steric really isn't an issue. We're pulling off your beta hydrogen and making a pi bond and kicking out your leaving group on the adjacent carbon. The more substituted your transition state is, the lower the energy. And so if your activation energy is low, you're going to go through a lot faster. So tertiary is always going to be more stable transition state than secondary than primary. Now, the second part is your X group. That's your leaving group. How do you know leaving group ability? There really are no guesses here. You just look at the pKa chart. Lower the pKa of the conjugate base, the better the leaving group ability. It is low because they're more stable and they want to be here, which is why they're dissociating more and your Ka is high and therefore your pKa is low. So the lower the pKa, the more stable the leaving group, and therefore the faster it's going to break and leave. So iodide would be more than bromide, would be more than chloride. Fluoride's really a bad leaving group. So that's how you find out leaving group ability. What about base? So basicity and acidity can be determined by the pKa chart, right? So that's also kind of a no-brainer. There are 2 main things about the base. One is the pKa. The pKa should be higher than 11. So it's in this range. The higher the pKa, obviously, the stronger the base. It should be at least above 11. Some books may say 12. pKa should be at least higher than 11. Second thing is the size of the base. If the base is going to be very bulky and big, then it's going to pull off the proton that is more accessible on the beta carbon that is less substituted. If the base is smaller, then it would go for the one that's more substituted to give you a more substituted alkene. So there are two competing things here. Steric ability versus the basicity. If the base pKa is high, that's good, it's going to be fast. However, sterics play a role in which direction the pi bond is going to be abstracted. So here's just a model to show you. Let's say these are all hydrogens, and this is your carbon with the leaving group halide. If it's a chloride, bromide, or iodide, a halogen, or even oxygen, you know you're going to have lone pairs out here. So let's say your base comes in, this is, let's say, a hydroxyl. Well, it's not going to approach from this end because they're both lone pairs and they're going to be butting heads. So it's going to be coming in from the opposite side. It's also not going to come from the same side just because, again, there's repulsion and the orbital alignment won't be perfect. So therefore, it's going to go for the hydrogen that is going to be anti-periplanar. That is, it's going to be 180 degrees away. Therefore, you'll have a p orbital forming when you abstract this and a p orbital forming when this leaves. And so those p orbitals can coalesce to form a pi bond. So your hydroxyl kind of, wanders all around trying to find another hydrogen to make water, which is stable. And let's say this is tertiary. Really can't get in here. It's getting kicked out by all these groups. So it goes, okay, well, let me pull out this hydrogen. So it pulls out the hydrogen on the adjacent carbon. And this all happens at the same time, but I only have two hands, so I had to do it stepwise. It does not happen stepwise. They all happen at the same time, okay? That's something to bear in mind. It pulls out this hydrogen. Hydrogen comes out, and those electrons from the hydrogen then run in to make a pi, which means, you can't have 5 pairs of electrons on this carbon. It's going to be freaking out. So it's going to kick out the leaving group, and that's going to happen all at the same time, okay? So you'll have a alkene. Now the alkene, so here's a model of the alkene. So your leaving group left and left this p orbital behind. The hydrogen left from this end and left this p orbital behind, and they both come together. There's one pair of electrons from the hydrogen that then gets distributed between this pi orbital, okay? Again, I don't want to mislead you by the stepwise, demo, but I just have two hands, so I have to show you stepwise. But it all happens at the same time. It's concerted, just like an SN2. There are lots of parallels between SN2 and E2. Let's take a look at the transition state. The transition state has two things in it, a base and an RX. Let's say this is a hydroxyl, just like the way I showed you. The hydroxyl wants to have another bond. That way the former charge is going to be 0. All molecules like to be former charge 0. So it's going to come and pull off the hydrogen. So this one of these electrons is going to go towards that hydrogen. The hydrogen electrons, 2 electrons, then spread through a sigma bond between the carbon and carbon, and that is going to kick out a leaving group. I'm just going to put X. It could be chloride, bromide, iodide, whatever. Okay. In this case, let's say it's a halogen, so I'm putting 2 lone pairs there. Now here you can have other R groups or hydrogen, and here too you can have other R groups or hydrogen. You can see that this transition state is going to be electron deficient because the halogen's pulling electrons out of the system to leave as an X minus. So whenever you have electron deficiency in a transition state or even an intermediate, you want to have friends that can donate electron density to alleviate that pain of parting. Okay, so you're electron deficient. These are going to give or donate electrons to that carbon and to this whole system to make it lower in energy. So that's why tertiary is better than secondary, better than primary. Now there are also hydrogens and carbons here, and these can do hyperconjugation. In fact, that's a really very big effect. the hyperconjugation effect. So the more carbon-carbon bonds you have here, the better the electron donation due to hyperconjugation. Since this is polar, what do you think about the solvent? Of course, you would want to have like dissolves like, so polar transition state will be stabilized by polar solvents. So let's talk about solvents. Solvents, polar, okay, is good. Apolar or non-polar is not good. Polar will stabilize this better. Next question is, do you want Next question is, do you want polar protic or polar aprotic? There is an issue with having polar aprotic. Well, polar aprotic is actually faster than polar protic. However, if you have polar aprotic and this is a primary or a secondary, then it could do more than SN2. So that's why we typically use polar protic. This is one reason. Another reason is a lot of the bases, for example, if you take hydroxide, it's sodium hydroxide. Sodium hydroxide is typically not soluble in a lot of the organic polar solvents. It's very soluble in water. So you bring it in with water. Same with the methoxide and the ethoxides that we use. We take the solvent, which is like ethanol, and add to that the metallic sodium to make sodium methoxide. So you're always going to have some residual protic solvent. So therefore, the way the base is made, it's made in a protic solvent, so you will have a protic environment. You may think if it's protic, well, why is it not doing E1, SN1? Well, E2, because there's only one step and it's a transition state, is faster than E1, which is multi-step. So if you have a competition between E2 and E1, E2 will always win if you have a strong base, and the base should be, a strong base. Now, if you don't have a strong base, that's when E1 becomes important. So if you heat this up, then you would have more E2 than SN2. Why is that? Because when you have elimination, you have more side products which increase the entropy, plus delta S is going to then increase the minus delta G. So it's a thermodynamic effect, not a kinetic effect. So we have a choice between polar protic, polar aprotic. We will choose polar protic, especially for primary and secondary, just because that would prevent competing SN2. If you have tertiary, then aprotic is fine, because in tertiary, SN2 is going to be hindered. So I can say aprotic for tertiary. So therefore, if I do this, E2 would be more than SN2. In aprotic tertiary, you are only going to really get E2. Now, what about temperature? Well, you know that Arrhenius equation, which is K is equal to A e to the minus EA over RT, has got a temperature component in there. And it's a 1 over and a negative, which means your temperature goes up, your K will go up always. So your temperature is going to increase the amount of elimination. So as temperature increases, elimination will increase. E2 will increase, and so will E1. In conclusion, I'd like to say that rates of E2 eliminations depend on 1, the substrate, 2, the leaving group, 3, the base, 4, solvent, and 5, temperature. There may be others, but we are just going to focus on this. One little note about cyclohexanes. Different geometrical isomers can have different rates. Here's a trans versus a cis. Let's see which one's going to be faster. Now, this molecule has got a T-butyl group, the big huncho guy. And you know they don't like axial up or axial down. They just want to be on the side, lying down. So you got to make sure that the bulky group is going to occupy the equatorial position always, because it doesn't like to flip to the other side. So if you put the T-butyl group on the equatorial, where do you want the chloride to be? Axial or equatorial? Let's draw it out. So here is our cyclohexane, same rules as before for drawing them. Some things never change. And this is one of them. Your T-butyl group is going to be, let's say this is butyl. So 1, 2, 3, 4. So this is 4-chloro, 1-T-butyl cyclohexane. And it is a cis. Well, let's look at that. So as we said, we want our T-butyl to be equatorial because that's the big honcho guy. It doesn't like to be propped up or hanging down because it's going to be then bumping into these hydrogens and here. So let's put that group on the side like this. All right, we got our chicken feet out of the way. Where do you want your chlorine? Can you put your chlorine equatorial or axial for an E2? What do you think? Oh, hint, hint, right here. We said the H and X leaving groups must be diaxial. We really don't have a choice in that. If it's equatorial, it's not going to go because the orbital alignment is not going to be here. You got to have a p orbital here and a p orbital here, and they got to be parallel to each other. If you're equatorial, you can't make it parallel. So you got to have this chlorine axial. You may think, oh, chlorine's going to be unhappy. Well, that's okay because chlorine is smaller than this huge T-butyl group, which is going to be spanning all of this space and then bumping into everybody. So if you're going to have this axial, yes, then it would be faster. So this has to be axial. That's the key thing. You cannot do an E2 with an equatorial, at least in a reasonable amount of time. So cis, where they're both on the same side, is going to be faster. As long as you can flip this leaving group to axial and put a huge bulky group equatorial, you're good to go. It'll be fast. All right. Well, that kind of concludes our discussion on E2. So that's a lot to take in, guys. If you have questions, let me know. As I said, we covered a lot of different concepts here. So make sure you go over them. And if you've got questions, just holler. Talk to you soon. Bye.